Importantly, though, I mentioned we have a magnetic field around the Earth, right? That magnetic field takes and the and magnet. What is a magnetic field? Well, it is a field of magnetism, right, that can attract or repel other charged particles. Now, our sun is emitting what's called cosmic rays all the time, these high energy particles, such as alpha radiation, okay, that comes from the sun, and it would otherwise hit Earth, and we're on Earth, okay, so it would otherwise hit us. But what happens is because it's a charged particle, alpha radiation, things like that specifically are charged, they get caught up in the magnetic field, okay? And they get directed around Earth, okay? But they get directed into where our magnetic field lines converge. Where do our magnetic field lines converge? I just told you guys. The magnetic north and south poles. That's the whole point of the magnetic field, is that it has a beginning and an end, right? That's where the aurora borealis and the aurora australis are, right? They are at the magnetic north and south poles of the Earth. The reason why the sky lights up is because those high energy particles coming from the sun are being directed around those field lines into those poles, right, into the magnetic poles. And those high energy particles are crashing into atmospheric particles. When they do that, they emit light. The atmospheric particles emit light when high energy particles from the sun crash into them, and you get to see that pretty light as those like ribbons of light in the sky. Okay.
With that information, does that have a lot to do with the extreme weather changes in both parts?
In where?
The extreme weather changes on both parts. Like one's like really cold, Australia's more hot.
It's more like the relationship of where those poles are at in relationship to the sun. They're either pointing at the sun or they're pointing away, and because of the Earth's tilt, it happens to be the North Pole often points away or toward, and same thing with the South Pole. Yeah, it has some more of the angle of orientation for the Earth, the axis tilt for the Earth. That's what I think mostly matters. Not so much to do with the magnetic field in this case. But the magnetic field is what gives rise to those phenomena, those beautiful lights in the sky. So, but importantly, it protects us from like most of the high energy particles. We would not really necessarily be here if we didn't have that protection from the magnetic field and that protection from our atmosphere, okay? The sun sends us high energy particles. The stars around the sun, all the stars, the nearest star is 4 light years away, but it still sends us high energy particles. They all do. You can see light coming from the stars. That means some photons from the stars are getting to you, and the stars emit all kinds of things, and those can get to us too. And between all of that, our Earth, our buildings, and our own bodies, you have about 5,000 radioactive decay events in your body every minute. Okay, you have many radioactive particles in your body, and about 5,000 decay events per minute. Okay, all of that together gives you an average dose of natural background about 3 milligray per year. Okay, a milligray is a 1/1000th of a gray. So we get 3 milligrays, 3 pieces in 1,000 of a gray. Okay, we'd have to get 1,000 milligrays all at once in order to be at risk for death. Okay, which is why we don't die from natural background radiation, because it's extremely low. To put that into perspective, it takes about 15 chest exposures to equal the annual natural background exposure. If you have in your binders, you have a page like this that lists radiation doses to adults from common exams. You can look at chest x-rays, a radiograph of the chest, and in this case it's a little different, but something around 0.1 millisieverts. Okay? Comparable in this case to about 10 days of natural background. Okay. It would take, as they say in this text, about 15 chest exposures to equal the annual natural background exposure. That means if you got in 1 year, if you got 15 x-rays, 15 chest x-rays, you have essentially doubled your background exposure by adding on chest x-rays. Getting a suntan is more hazardous than a single chest x-ray. You get more than 0.1 millisieverts by hanging out in the sun for a couple hours. It's equivalent to driving in risk terms in risk analysis, it's equivalent to driving 4 or 5 miles. That's about as risky as getting a 15 chest x-rays or getting your natural background, or smoking a few cigarettes and then quitting forever. Okay. A single AP film of the abdomen is about 3 to 5 milligray. So a single abdomen film is worth about 15 chest x-rays. You can take away from that that chest x-rays are relatively low dose. Okay? But if you get a single abdomen film, you have gotten in a single setting, single image, what you would get in a year of natural background. Okay?
Is that because more of your organs
Yep.
in those areas is
Yep.
absorbing the X-ray?
Absolutely.
Because of the concentration of the organs?
Absolutely, like denser tissue, right? And what do you need to do with the x-ray beam when there's denser tissue?
Power it up more.
Higher kV, right? And more of it, right? More mass, more kV. Where a chest x-ray, it's largely lung tissue, and lungs are largely air, gas, and x-rays pass through gas, no problem, right? So you get high kV, yes, but extremely low dose, like 3 to 5 mass for a PA chest. Where an abdomen, you're going to be shooting at like 80 kV, so lower kV, but importantly, your mass is going to be like 80. 80 at 80 is a really common abdomen technique, and 80 mass is significantly more, right, than 5 mass is, right? So yeah, you get more exposure, much more exposure with a single abdomen than you would get with a 15 chest x-rays, right? Let's look at some other units here. Now these are different. Like if you look at here, this is saying 0.1 millisieverts for a chest x-ray, right? And on here they're saying 0.2 milligray or millisieverts for a chest x-ray. So you're going to get slightly different numbers, and that's because the numbers will differ slightly. Everyone's chest settings are a little different, and the way we can calculate it can be a little different. But what you should take away from this is like the ballpark of comparison here. Okay, so 3 Mile Island, high-end exposure. These are the people living nearby to 3 Mile Island, the nuclear power plant. 15 microgray, not milligray, microgray. That's a millionth of a gray. 15. Okay, equivalent to smoking 0.2 cigarettes. You take a couple of puffs off a cigarette. That's what the people who lived around 3 Mile Island basically did. That's the risk amount that they. It's equivalent to driving a half of a kilometer. A little bit, drive down the road. That's the same equivalent. Or 2 days of natural background. So that year, when 3 Mile Island happened, those people basically got 2 extra days of natural background radiation by receiving the radiation from the meltdown. Single PA chest, 2 cigarettes, or 6.4 kilometers driven, or 3 weeks of natural background. Okay, so it has to be taken with some consideration, right? You're increasing people's radiation dose when you give them a chest x-ray. Give them an abdomen. That's equivalent to smoking 40 cigarettes. I don't know if you know how many cigarettes are in a pack. It's usually 20. That's 2 packs of cigarettes. Okay, so smoke 2 packs of cigarettes or drive 160 kilometers. Those are the things that are as risky as a single abdomen x-ray. And that's not even the high end. Okay, you look at the one next, 2 down, shown in kind of a bright green, barium enema series. Okay, 120 to 150 milligray. 10 barium enemas have enough radiation to cause severe damage to the body. You're not going to get 10 of them. Okay, you're just not. You're going to get 1 of them. Okay, equivalent to 1,200 cigarettes smoked, or 4,800 kilometers driven, or get this, 40 years of natural background in a single X-ray study. So, not to be taken lightly, right? You want to do a barium enema when it's medically necessary, when the risk of doing it is outweighed by the benefits of doing it, right? The risk of doing it is giving this person 40 extra years of natural background, where the benefit might be we discover that they have colon cancer. Okay, so they got a big benefit, right? Chernobyl survivors. The people that survived, not the people that were, not the like 100,000 that were vaporized instantly, but the people that survived, 450 milligray, equivalent to 3,600 cigarettes, or this is the number that always is impactful, 150 years of natural background radiation. And it wasn't just in the single instance where the bombs exploded. That's Chernobyl, but the power plant exploded. Let me go down to Chernobyl. Let me go down to Hiroshima, excuse me. Hiroshima bomb survivors in Japan. 700 years of natural background exposure. Those are the survivors from that. 2,000 milligray, that's 2 gray, right, which is enough to kill you, right? 1 gray is enough to kill you. Equivalent to 64,000 kilometers driven or 16,000 cigarettes smoked. And this, again, what I was trying to get at is this isn't just in the initial blast, right? Radioactive elements stay radioactive for as long as their half-life is. And some radioactive elements have half-lives that are billions of years long. Okay, most have half-lives in the thousands of years or the hundreds of years or the tens of years. But importantly, these people were exposed to those radioactive elements and continue to be exposed to those radioactive elements if they stayed in those areas. Okay, because those elements don't go away, right? Like Chernobyl. When Chernobyl blew up, they had to evacuate the entire city of Pripyat, which is the city that basically fed the power plant with workers, and they had to evacuate the entire surrounding areas and make this big exclusion zone around the power plant, a big radius around the power plant, where they actually had to go in and they actually had to kill all the animals that lived there, so the animals couldn't make more animal babies that were radioactive babies, and they had to take turns working in there so they didn't get too much radiation exposure. Lots of people died because of it, and they had to decommission tons of equipment. They just left the equipment behind because the equipment is covered in radioactive material now. Okay. And there's this ginormous exclusion zone around Chernobyl because of the fact that those elements don't go away. There's a lot worse stuff to it that we can talk more about later. That was a true disaster, and it's still affecting the world to this day. But the point is, it gives you some perspective on, what is normal, right? What's our normal is like 3 milligray per year, okay? In these radiation disasters, people were getting 2,000 milligray in a single instance and potentially surviving that. Others die. But they're getting many lifetimes of worth of natural background in single exposure events in these disasters. So those we want to, of course, avoid, but it gives you some perspective on what's normal versus what's a disaster level. Okay. Great, so now we have a little bit of range for comparison, right? So the very wide range of exposures that can be delivered to a patient in diagnostic radiography extends from procedures that are almost negligible in their exposure levels to those that are of serious concern. You can cause some radiation syndromes, such as the nausea, vomiting, diarrhea syndrome, from diagnostic exams, right? There are exams we could do in an x-ray room that could potentially give somebody serious health effects from it. So physicians have to weigh the risks and benefits of doing these exams. Because of the cumulative risk of exposure over time, regardless of the risk level for each procedure, something called the ALARA philosophy is always followed by radiographers. Has anyone heard this before? ALARA? Parrish, what's it mean? So burn this into memory. It stands for as low as reasonably achievable. Okay, it is one of the most important acronyms you have to remember in radiography. ALARA. Okay, that means keep your dose to patients, to staff, to yourself as low as reasonably achievable at all times, and you can't go wrong. Okay. How are we feeling so far? It's a lot coming at you. Okay, we're about a third of the way into this. Okay, for today. So we've got a lot to learn. It's a big learning curve. I'll give you that. But it all is important. It's all important. What you're going to need to do, right? You're going to need to have read the material before you came to class today. That's important for one. Do the homework. That's great. But importantly, you've got to go back through this material multiple times. Okay. If you're not doing that, if you're not giving yourself, unfortunately, 2 to 3 hours per day, faces in the books, then it's not gonna click. Okay. Watch the YouTube videos for reference. Read everything that I give you, right? And review. okay, as much as you can. That's going to be helpful for us in the coming days because there's a lot of technical information. I'm trying to put it out to you guys in a way that is easily understandable, but it's still a lot. I remember learning this stuff, and it's a lot. Okay, so I'll give you that. But with that said, you guys can do it. I know you can. Okay, and let's keep going. So